Okay, so the revised title of this talk is Orderable Groups and Feynman's Theorems, and it's based on the following principle. Spinoza wrote it as hollow vacui, nature abhors a vacuum. Evidently, in one of his books on physics, Aristotle wrote that you can't have a vacuum in nature, because if there were a vacuum, everything surrounding it would rush in and fill it. So we had a vacuum in today's seminar schedule. So I had to fill it, and I had asked for volunteers last week, and bereft of a volunteer, I thought I had to talk. So I'm just filling the vacuum. So this is not the.
Well, you said you had something you were hoping to talk about for Heisenberg groups, right?
Well, that was going to fill the vacuum, I thought, but that seems to be a lot more complicated than I might have thought. Anyway,
would you consider giving us a talk about the complications at some point?
Well, there are a lot of complications that have to be resolved before I can even say what the complications are. So, but the origin of this is the following. At some point early in the semester, I gave a talk about Freeman-Dyson's method in improving Schneermann's theorem and Mann's theorems on the density of some sets for sets of integers. And I said that there wasn't a way to do this yet for sets of lattice points. And then somehow at random, I found on my computer some notes that I had written 10 or more years ago, which actually had the result for sums of sets of lattice points. And when I looked at it, I realized that all it really used was the fact that there was a way to order the lattice points. So if you look at the group Z plus Z, it's an ordered group. So I got interested a little bit in ordered groups. And as it turns out, they're actually much more interesting than I had realized. So I'm going to just mention some results about ordered groups, and then go to some of Feynman's earliest theorems, inverse theorems, and additive number theory. So we have a group G, with identity E, and a left order on the group is a total order where if X is less than Y in the group, and you take any element G and you multiply X and Y on the left by G, if X is less than Y, then GX is less than GY. So we say the group is left orderable if there exists a left order on it. And there's no reason why left is preferable to right, so you can also define a right order. So there's a right order on the group. There's a total order. So that whenever X is less than Y, and for any G, if you multiply on the right, XG is less than YG. And so we say the group is right orderable if there exists a right order on G. And if you have a two-sided order or a bi-order, usually we just call that an order. So an order, a group is orderable if there's an order on the group which is simultaneously a left order and right. And we say that an element in a group is positive if it's strictly greater than the identity, and negative if it's strictly less than the identity. So what are some examples? A vector space over the rationals or over the reals. These are orderable additive groups. Torsion-free abelian groups are orderable. Torsion-free nilpotent groups are orderable. My favorite group, the Heisenberg group, is a torsion-free nilpotent group, so it's orderable. And there's a famous construction of Maltsev and independently of Philip Paul that three groups are orderable. Many groups are orderable. And there are two very good references that I found that are on archive. So these are really books, but the whole books are on archive. One is order groups and topology. The other is groups, orders, and dynamics. And this is to indicate that there are a lot of connections between ordered groups and problems in topology and problems in dynamical systems. I mean, I was really kind of surprised to see how interesting and important the ordering of a group can be. So,
Just before we move on, if there's so many ordered groups, can you give an example of a non-ordered group?
well, a simple example, I mean, I'll say this in a moment, but an ordered group has to be torsion-free.
Right, so finite groups, torsion groups, but something which is torsion-free.
So, yes, I'll give an example. Actually, I think in these slides, I have, well, we'll see, we'll get to that, but there certainly is an example of something which is not ordered and is definitely torsion-free. So, in a left-ordered group, the product of positive elements is positive. The product of negative numbers is negative, and an element is positive if and only if its inverse is negative. So, yeah, so this is half of a lemma. If you have a family of sets x sub I, and each of them is totally ordered, you can totally order the product set lexicographically. That means if you take two sort of vectors, x and y, that are different, to say they're different means that there's some coordinate xi and yi that are different. And because the index set is well ordered, there's a smallest element I1, where xi1 is different from yn. And so you define x to be less than y if the first coordinate where the vectors differ, x of that coordinate is smaller than y in the other coordinate. So that defines an order on the product set, and if xi is a group which is left ordered or right ordered or totally ordered, in the natural way, this makes the product set ordered. So what's supposed to be, oh, actually it's the next lemma, sorry. So if you have a left ordered group, every subgroup is left ordered. A product is left orderable. For that, you can just use the lexicographical ordering I just defined. The direct sum of groups is left orderable groups is left orderable because the direct product is ordered, and the direct sum is a subset of the direct product. Okay. You say that a group has unique roots if whenever x to the n equals y to the n for some positive integer n, then x equals y. So a simple thing one can show is that every left-ordered group is torsion-free, and if the group is ordered, it's torsion-free. It's actually a more generalized version of torsion-free, but that has unique roots. So, and if a group is ordered, it has unique roots. So one way to show that some torsion-free group is not ordered is to show that it doesn't have unique roots. We'll do that in a moment. So if you have a group that's ordered, the elements bigger than the identity are positive, the elements less than the identity are negative. And what is called the positive cone of the order is just a set of all positive elements. And if x and y are positive, and the group is left ordered or right ordered or ordered, but in one-sided ordering is enough, the product of two positive elements is positive. So this positive cone is a sub-semigroup of the group. And the set of negative elements in the group is the set of inverses of the positive elements. So whenever you have an ordered group, you have a partition of the group into this semigroup P, which is positive, the identity, and the semigroup P inverse, which is the set of negative elements. And there's a converse which says the following, though you have to be a little bit careful about what it is. If you have a group G, and you can write it as P union E union P inverse, that's a partition, where P is a sub-semigroup. You can define X less than Y if X inverse Y is in this positive semigroup. And that defines a left order in the group, and the semigroup P is this positive thing. So there's something like a one-to-one correspondence between partitions of a group into a semigroup, the inverse of the semigroup and the identity, and the set of all left orders on the group. And this left order, defined by a semigroup P, is an order if, in addition, every conjugate of the semigroup is contained in the semigroup. So if and only if G inverse PG, this should be a lowercase g, is contained in P for every element. Group extension. So this is really very useful. If you have a short exact sequence of groups, so this means A is a subgroup of G, and B is G mod A, basically. If A and B can be left ordered, then G can be left ordered. And if A and B can be ordered, then G can be ordered. So this is really very useful. This gives you a way to construct ordered groups if you can take a group and show you can decompose it in this way. So there's a subgroup A and G is B mod A. G mod A. So this property of being left ordered is local. I mean, for almost everything I'm talking about, I've actually sort of written out proofs in detail, but proofs aren't very good at seminars. And plus, in some sense, this is all standard. There's nothing in this talk which isn't known to everyone who knows it, basically. So if G is a group with an identity, if you look at this set of all non-empty finite subsets of G minus the identity, so there's like its following technical conditions. The group G can be left ordered if and only if every one of these finite subsets, there is a way to map the elements to plus or minus one, such that if you take the sub-semigroup generated not by the elements of K, but either by the elements or by their inverses. So this epsilon K, this is either plus one or minus one. So for each element of X of K, I'm either choosing X or X inverse.
You're flipping the sign, so to speak. If it so happens that the elements don't all share the same positivity or negativity, you're flipping the ones that are wrong. Yeah.
Well, yes, retroactively, right? Because G is not ordered, right? Sorry. So, well, I mean, in one direction, yes, in one direction, you're just choosing the positive elements. But the point is that if there's a way to choose the plus or minus signs, such that for every finite set K, such that this set of cardinality of K elements doesn't contain the identity, then you can left order the set. And from that,
This
one
is
can
another
show
one of those
that,
theorems, like if every finite subset has a solution, then the whole system has a solution.
right, but this isn't exactly every finite. If every finite subset can be massaged in this way, then yes, then the group has an order, a left order. So you can say the group then is left orderable if and only if every finitely generated subgroup is left orderable. And the group is orderable if and only if every finitely generated subgroup is orderable. And one proves this in the usual lazy way to prove a theorem of this sort. You construct some compact space, then you prove that this finite condition gives you something like a finite intersection property, and the infinite intersection is then not empty because the space is compact and the sets are closed, and you get this choice of epsilon k that works for the whole group. But it's the locality property that's just interesting. But a group, and I have no way. If you ask why is this true, to say that I can give a proof is sort of irrelevant. But I don't know why it's true. I don't have any feeling for this, but it is just a fact of nature. Okay. So there's some the geometry is irrelevant. If there's something called a Klein bottle, it has a fundamental group. The fundamental group is an infinite group which has two generators, x and y, and one relation. That is, if you conjugate the generator y by the generator x, you get y equals. So this finitely presented group is the group on two generators with one relation. That's my G. And this group has lots of beautiful properties. First of all, if you have y-x is xy inverse, if you take any product of two elements, where the first is y or y inverse, and the second is x or is x inverse, you can flip them around by these rules, which means that every word in x and y can be written in the form x to the k, y to the k, y to the l, with some k, l, and z cross z. And you can show that this group is an extension of z by z. So z, the additive group z, is ordered. 1, 2, 3, 4 is an ordering. Actually, there are two orderings on z. Either the positive elements are 1, 2, 3, 4 in that order, or the positive elements are -1, -2, -3 in that order. So there are exactly two orders on the integers, but it is left orderable. And so this group is left orderable. But so you do a little algebraic calculation. Y-axis, no, that's backwards. It should be y-axis xy inverse.
What do you mean by an extension of z by z?
So the group G, so if you have a short exact sequence, AGB, like this, so the G is called an extension of A by B.
Got it. Okay.
So A is a subgroup of G, a normal subgroup, and G mod A is B. This way, y-axis xy is, yeah, it's xy inverse. So X and Y are the two generators of the Klein group. And this is the one relation they satisfy, which gives us these identities. So Y-axis xy inverse. So let's see if I did this right. Y x squared is,
That thing in the middle is wrong, but it is equal to xy inverse x. That's correct.
so y, sorry, I get to the, I'm trying to do this. It's not. Okay, so yx squared is y x times x. So that's xy inverse x, which is x. What is it, 60?
That's the relation?
No. Let me just, I extracted this from,
Isn't that the relation from the group presentation?
so, well, everything comes from the presentation. So yx squared is xy inverse x. Hmm.
And in the group presentation, y inverse is what you have in the parentheses.
I want to get this last line, which is yx squared is,
In the last line, just replace first of the yx by xy inverse, and you get it.
right, yes, I mean, exactly, yes. Which is yx xx inverse it's yx squared is yx times yx, and I stuck in an xx inverse. So that's yx squared x inverse yx. But x inverse yx is y inverse. So this is yx squared is supposed to be x squared y. That's what I'm supposed to get in this first line.
It's so much easier if you just say yx times yx, and then the left of these yx you replace by xy inverse.
Yx. Well, all I want is some
So you get-
comparison to the notion that from these relations, I get that yx squared is equal to x squared.
Yes, in
And
fact,
that
in
means
fact,
that this group does not have unique roots.
yeah,
right.
the group can actually be presented, I think, in terms of, a squared equals b squared. I think you can take that as a relation.
No, I don't know what. Let me just take a piece of paper. So yx squared is xy inverse x, which is x y inverse x is xy. Yeah, okay. So yx
yeah.
squared.
Alexander has posted a shortest possible derivation.
That's I just want to get what I wrote down to be correct. So this is xy inverse x and y inverse x is x. Y inverse x is xy. So this is x times xy, which is x squared y. Okay. So now this is okay. So yx squared is yx is xy inverse. Y inverse x is xy. So yx squared is x squared y. So yx squared is x squared y. So I get x squared. So yx is different from x, but they have the same squares. So the group does not have distinct roots. So the group is not orderable. So this Klein group, xy with this relation, is an example of a group which can be left ordered but not right ordered. That's it. That's it. Okay. I'm just mentioning a few things about ordered groups, which I certainly had not known, and it's part of things that the things I just find very interesting. So, if you have a left ordered group, it can be bi-ordered. If and only, that means there's a two-sided order which extends the order. If and only if x less than y implies y inverse is less than x inverse for all x and y. That's right. And there's the following very interesting result, which says that if you have a left orderable group, it's abelian if and only if every left ordering is a bi-order. Okay. Let's get back to number theory. So, Freiman has a lot of theorems that are inverse theorems, and they have the following flavor. You have a set of integers, positive or negative, zero, doesn't matter. You have k integers. You look at the sum set S plus S. And the theme of Freiman's work on inverse problems is that if the sum set is small compared to S, then S has some structure. So if you have some sort of exotic set, the sums are going to be not going to have many overlaps or coincidences. But if the sum set is small, the set has to have structure. The following results are due to various people, Freiman, Herzog, and so on. Usually these papers involve Freiman, Herzog, Longobardi, and Maj, and some also, and those four are like part of every paper. And some also involve Lenclan, Robinson, Stanchevsky. So if you have any set of k integers, the sum set has at least it'd be nice to get things correct.
Should be a minus, yeah?
At least 2k minus 1 elements. Yes. And a very simple theorem says that the sum set has exactly 2k minus 1 elements, if and only if the set is an arithmetic progression, which is a kind of convexity condition, because if you take your set S of integers, if you translate it, you're not going to change the structure or the size of the sum set. And if you contract or dilate it, you also don't change the structure of the sum set. So if you have a set of integers in arithmetic progression, you can translate it so the smallest element is 0, and you can contract it by dividing by the greatest common divisor of the elements. So you end up with an interval. So this is essentially like saying that if your set S has the smallest possible subset, your set S is the set of integers inside of some convex body in the line, which is just an integer. And one of Feynman's first theorems, okay, sorry, forget that. That's the thing. In a non-abelian group, if you want to consider the analogous thing to a subset, you generally write the operation as multiplication. So we're looking at the product set. So instead of looking at all sums of two elements of this from an additive group, we're looking at the set of all products of two elements from this subset of the multiplicative group. And there's the following very nice theorem. This is actually, I believe, a theorem of the torsion field groups, Brailovsky and Feynman from a rather long time ago. But the thing is, it turns out that a lot of these theorems about integers use nothing more than the fact that the integers are ordered. So you can carry them over to an ordered group, generally not a group. So if you have an ordered group and a finite subset of k elements, the product set is as small as possible. The product set is always going to have at least 2k minus 1 elements. And you're going to have exactly 2k minus 1 elements. If and only if your set is a geometric progression, that is a set of the form y times x to the I goes from 0 to k minus 1, and the x's and the y's commute. And of course, it follows immediately that if S is this geometric progression, then the subgroup S generates is generated by y and x, and it's going to be an abelian subgroup. But in this multiplicative case, if you're sitting in an ordered group, to have the smallest possible product set means that your underlying set is simply a geometric progression. Now, Feynman developed this a lot further. So if you have a set of k integers, and the sum set has at most 3k minus 4 elements. So if you have k integers, the number of sums is, if they were all different, you would have order k squared over 2 elements. So this sum set would be quadratic in k. If it's linear in k, and in some sense not even too linear, no bigger than 3k minus 4, then your set is no longer an arithmetic progression, but it's almost an arithmetic progression. It's a fairly large subset of an arithmetic progression. An arithmetic progression will have the most 2k minus 3. And you can refine this a little bit. If the number of elements in you have a set of k integers, and if the number of elements in the sum set is 2k minus 1 plus b, b is how much bigger it is than the smallest possible sum set. But still no bigger than 3k minus 4, then S is a subset of the arithmetic progression of k plus b. And the point is that this carries over to product sets in an ordered group. So if you have an ordered group G, and a subset of G with k elements, if the product set has at most 3k minus 4 elements, then there exists commuting elements x and y in the group, such that S is a subset of the geometric progression of length, size of S squared minus S. In particular, this is at most 2k minus 3. So if the product set has at most 3k minus 4 elements, then your set S is contained in a geometric progression of length at most 2k minus 3. In fact, you can actually improve one thing slightly. If the product set is one bigger, 3k minus 3. So in this case, the set S clearly generates an abelian semigroup because the x and y, even if this were one bigger, you would get an abelian semigroup.
So, Mel, the top two theorems are Feynman. Who is responsible for this third theorem?
Everything is Feynman and his mafia.
Okay.
So that list of names I put up at the beginning of this section, Freiman, Herzog, there were two Italian women.
Longobardi
There's
and
a British
Maj.
guy named Robinson, another Israeli named Francesco. This is all their work. So this is the 3K minus 4 theorem. So if your product set has the most 3K minus 4, your set is contained in a geometric progression that's fairly small. All right, well, suppose it's not, the product set is not 3K minus 4. Suppose it's 3K minus 3. So, so Freiman long ago had proved a theorem about this for the integers. If the sum set is at most 3K minus 3, then your set of integers is either contained in an arithmetic progression or is contained in the union of two arithmetic progressions with the same difference. And that's exactly what one has here. If your product set is no bigger than 3, I mean, it's really only interesting if your product set equals 3K minus 3. Because if it's 3K minus 4 or less, you have the previous thing. So the group is generated, so the group generated by S is abelian. And there exist commuting elements X, Y, and G. So that either S is contained in a geometric progression, and you have this 2K minus 1, 2K minus 1. Or S is the union of two geometric progressions with the same difference.
Probably worth mentioning it. This isn't just in theory. That is to say, this is as sharp as it gets. You have specific examples where this is exactly what happens.
Yes, absolutely. There's actually one other exceptional case, but it's special. This is suppose you have an ordered group. It should probably should probably be 3K minus 2. Otherwise it doesn't make sense. So if S squared is 2K minus 3, we just had a theorem. So this should be S squared is 3K minus 2. All right. Oh, sorry, no, this is right. This is a theorem I'm looking at. And this is really the last theorem I'm going to discuss. So if S is a subgroup of G with K elements, and the product set is 3K minus 2, then Freiman and company have analyzed this. And there are the following possibilities. So one is that S generates an abelian group is generated by most 4 elements. The structure is not so easy to describe. It could be that S doesn't generate an abelian group, but it generates a nilpotent group, or a 2-element nilpotent group. It could be that S is what is called is a special case of the bounce-log solitaire groups, which are local to the graduate center. So this is a 2-element, a group generated by 2 elements A and B, where the conjugate of A is A squared. And there are 2 other special cases. Anyway, the moral of the story is that we have another instance where there are results in additive number theory about the integers, but the essential fact about the integers that's used is simply the ordering of the integers. And these results have analogs in very in arbitrary ordered groups. I mean, if you look at the literature, you'll see that Green and Tao and the French guy whose name I am forgetting, have lots of papers on analogs of Freimon's theorem in torsion-free no-potent groups. And torsion-free no-potent groups are all orderable, but they have additional properties as well. It's just interesting that there is the extensions of Freimon's theorem to group theory seem to work in many cases in a very straightforward way for ordered groups. To prove these theorems is not so hard if you just look at the theorems on the integers and do a kind of translation. It took some cleverness to think of going into the domain of ordered groups. But once you have that idea, it's in many cases the work is, there's some work, but it's more or less straightforward to get the results. So this is just not something I find rather curious. That the ordering comes up in additive number theory in some natural ways. And that is all I have to contribute to the vacuum that needed to be